So in this video, we're going to look at how to find the mass of a lamina over a surface. So now we're not in the plane. Now we're laying our thin sheet over some kind of volume. And so essentially we're involving surface area. Now the formula to find the mass of a lamina over a surface is the density function integrated over the appropriate region, d capital S. So that's our surface integral component. So let's look at our example. We're going to find the mass of the lamina over the surface that is given by, in this case, this is a paraboloid. Inside the cylinder, x squared plus y squared equals 16. So we're inside that boundary, bounded by the coordinate planes. So we're only looking at the first octant, and the density varies according to the function x squared y. Now, the coordinate planes are going to restrict us to that first octant, first quadrant in 2 dimensions, but the first octant in 3 dimensions. So we're going to find the normal vector to the surface and then find its magnitude for our ds function. Since our surface that we're looking at is x squared plus y squared, we're going to put everything on one side of the equation, get our big G function, and then find the gradient. So everything on one side, so z gets moved over, and then we find the gradient by finding the derivative for x, the derivative for y, and the derivative for z, and that gives us 2x for the derivative for x, 2y, sorry, that's a typo, for I fixed it down here, the derivative for y, and then the derivative for z, which is -1. And then the magnitude of that, again, repeating typo, but fixed right here. 2x quantity squared is 4x squared, 2y quantity squared is 4y squared, plus -1 squared is +1, and then times dA. That's our d big S component. And then we're going to need to convert this to polar coordinates because we're inside a cylinder, and so our boundaries are actually going to be dependent upon it's going to be easier for us to work with if we're in polar coordinates instead of rectangular coordinates. So if we switch this out, 4x squared plus 4y squared is 4r squared plus 1. And then our function, our density function, will also have to be converted to polar coordinates, again, equivalent to cylindrical coordinates. So x is r cosine theta, so x squared is r squared cosine squared theta, and then y is r sine theta. So, and then we also have dA from up here is r dr d theta. So that gives us r squared and another r, that's r to the 4th, cosine squared theta sine theta, and then our component of the ds out here for the arc length. And then we set our limits of integration. We're inside the cylinder of x squared plus y squared equals 16. So that gives us radius, a circle of radius 4. And since we're only in the first quadrant in the plane, then our theta integral, theta limits are 0 to pi over 2. Now we can switch the order of integration here since the sine and the cosine don't really interact with each other, the theta and the r don't really interact with each other, and our limits of integration don't depend on each other. They're constants. So we can switch the order of integration and do theta integration first. This will be a simple substitution. We would let u equals cosine, du would be negative sine, and then we will have just an integral in terms of r alone. So we would end up with again, u squared as our substitution, or negative u squared, and then you integrate that, you get -1/3 cosine cubed, and you plug that in. Now, integrating this bad boy is going to take quite a bit more work. in order to do it by hand, you would need to do something like trig substitution. And I omitted that step manually. But that if you were having to do it by hand, that's what you would have to do at this point. A substitution is not going to work here. And I believe, based on experience, this r to the fourth is going to be a problem for just trying to do integration by parts several times, because you're going to end up at the end with just the square root by itself. And that's not, so that you're still going to end up having to do trig substitution anyway. So you might as well just get it over with. And when you do that integration, what you end up with is this really nasty expression, or you can do it numerically. Since we do have limits of integration, that is a potential option depending on what the requirements for your specific problem are. And then you can at least get an approximate value that's reasonable. Now, the one thing kind of be cautious of here is, unless your problem is chosen very, very carefully, you're often going to end up, particularly if you have crazy density functions, you're often going to end up with situations like this where even if you can integrate one of the variables, any variable that's left under your radical here is probably going to be harder to integrate. Again, if you choose your density function carefully, then you may be okay in terms of doing it by just integration by parts. But in this case, we ended up with something that actually can't be done by parts. It has to be done by trig substitution. But again, that's going to vary from problem to problem. And textbook problems usually are set up in a way that you don't necessarily have to go to some of these more advanced techniques.